You've probably seen the footage. A plane takes off, hits a bird, and a ball of fire erupts from the back of the engine. Every instinct says the engine just caught fire, that the bird smashed through the blades and something critical is burning. That's exactly backwards. That fire isn't the engine dying, it's the engine saving itself. And what makes that possible starts with something about the collision itself that most people never consider. At 300 miles per hour, the bird isn't a solid object. If you've been sitting near the wing during a bird strike, you know what it sounds like. Not a splat, not a crunch, a single sharp bang, a metallic thud that vibrates through the floor and into your armrest. What's happening behind that sound is stranger than the force alone. A Canada goose, one of the most common large birds near airports, weighs about 8 pounds, roughly a gallon of milk. When that 8-pound bird meets a fan blade at takeoff speed, it generates over 70,000 pounds of force on a single blade. The weight of a fully loaded semi-truck concentrated onto an area smaller than your hand in under 2 milliseconds, about 150 times faster than you can blink. 70,000 pounds sounds like it should snap any blade ever forged. And if it does, the problem doesn't end with one broken blade. A multi-ton fan disc spinning thousands of times per minute with a blade suddenly missing becomes catastrophically unbalanced, enough vibration force to tear the engine from the wing. The force only gets worse with speed. Kinetic energy scales with the square of velocity. So a 20% increase in airspeed doesn't add 20% more force. It adds closer to 50%. That speed limit of 250 knots below 10,000 feet also happens to keep aircraft inside the engine's certified bird strike envelope, in the exact altitude band where most birds fly. But the force isn't the strangest part of this collision. At 300 miles per hour, the bird doesn't behave like flesh and bone. The impact forces so completely overwhelm the structural integrity of biological tissue that the bird stops acting as a solid object. It effectively behaves like a dense balloon of water detonating against the blade surface. In the first microsecond of contact, the fluid decelerates against the airfoil, generating a localized pressure spike in the tens of thousands of psi. Then the liquid spreads, flowing outward across the blade at hundreds of miles per hour. Calling an animal a fluid sounds like physicists' shorthand. It's the actual design parameter. The Wilbeck model, the standard mathematical framework for bird strikes, developed in the late 1970s and still in use, treats the bird entirely as a hydrodynamic projectile. At these velocities, bones and beak provide essentially zero structural resistance. The blade isn't facing a solid impact, it's facing a fluid shockwave, and that distinction drives every material choice and every countermeasure inside the engine. Most people picture a jet engine as a high-speed blender. The massive fan blades spin fast enough to chop the bird apart. The remains get incinerated in the combustion chamber, and the engine keeps running. That mental model feels right because it matches everything you've experienced with spinning blades, blenders, lawnmowers, propellers. And the fan blades do slice through the bird. That part is accurate. But biological material reaching the combustion core doesn't burn up harmlessly. It chokes the engine. It displaces the oxygen the combustion chamber needs, disrupts the carefully balanced airflow, and can extinguish the flame entirely. The bird reaching the fire isn't survival. It's how the engine dies. And the blade itself? If it were solid metal, rigid, dense, unyielding, that fluid shockwave would snap it. Rigidity concentrates the entire force at the point of contact. The blade fractures into shrapnel. The engine doesn't survive by overpowering the bird. The actual engineering works differently, and it starts with something visible from your seat at the gate. Next time you board and glance into the engine, look at the fan blades. That silver leading edge catching the light is titanium, or on newer engines, hardened steel. Its job is to slice incoming fluid and protect what's behind it. The dark matte surface curving behind that leading edge is carbon fiber, and the reason it's there traces back to one of the most expensive lessons in aviation history. In 1968, Rolls-Royce tried building the first composite fan blades for their RB211 engine. They were lighter, allowed a bigger fan, and performed perfectly under normal flight loads. Then engineers fired a bird at them. The composite layers peeled apart on impact, delaminated, shattering the blades, and destroying the engine core. The failure nearly bankrupted the company. The problem wasn't carbon fiber. It was the architecture. Early composites were laid in flat, two-dimensional sheets. A hydrodynamic shockwave hit those sheets, and they separated like pages in a wet book. The fix took decades. General Electric cracked it first, certifying the GE90 with composite fan blades in 1995. On the newest generation, the CFM Leap, the GE9X, the architecture went further. Carbon fibers are woven in 3 dimensions using industrial looms, locked together through the full thickness of the blade so they physically cannot peel apart under impact. A glass fiber trailing edge, softer and more flexible than the carbon structure, absorbs the residual shock and prevents cracks from propagating into the main blade body. The titanium leading edge distributes the initial fluid hit. The result? The blade takes 70,000 pounds of hydrodynamic force, flexes, absorbs the energy across its full span, and springs back. In over 100 million flight hours on GE composite fan blades, not a single one has failed from a bird strike. But surviving the hit is only the first problem. The shredded fluid is now inside the engine, and if it reaches the combustion core, the engine flames out. So the engine sorts it. Modern turbofans push 90% of their intake air through a wide outer duct that wraps around the core. Only 10% enters the core where fuel actually burns. Just behind the fan, a structural ring called the splitter lip divides these 2 paths. Because the liquefied bird is far denser than air, the spinning fan flings it outward. Centrifugal force handles the separation. The heavy debris enters the bypass duct and exits the rear of the engine without ever reaching the combustion chamber. That bypass duct wasn't designed for bird strikes. Its primary purpose is fuel efficiency. Routing air around the core generates thrust more economically than forcing it all through combustion, but it doubles as the most effective biological debris separator ever engineered. Everything covered so far, blade flex, centrifugal sorting, handles the bulk of the impact. But centrifugal separation isn't perfect, and the engineering that manages what slips through is where the real sophistication lives. If this kind of breakdown is useful, subscribing takes 1 second. A fraction of the fluid, especially from a large bird, inevitably enters the core. That's why passengers sometimes catch a sharp, acrid smell through the overhead vents moments after a strike. And that fraction triggers the most dangerous phase of the engine's survival. The dense fluid displaces the air entering the high-pressure compressor. The compression ratio, normally above 30:1, collapses. With too much fuel and not enough oxygen, the airflow reverses violently. Engineers call it a compressor surge. Excess fuel ignites as it blasts out the exhaust. That's the fireball passengers see from the window. Excess fuel, igniting because the combustion chamber suddenly can't burn it fast enough. From a window seat, that distinction feels academic. Fire is fire. But to the engine, it's the difference between a recoverable disruption and total failure. Left unchecked, the surge would kill the engine in seconds. But the engine's central computer, the FADEC, detects the pressure drop and the temperature spike within milliseconds. It pivots variable vanes inside the compressor, changing the angle at which disrupted air meets the spinning blades. It opens bleed valves to vent the surging pressure into the bypass duct, forcing the engine to cough out the blockage. And it fires the igniters continuously, keeping the combustion flame alive until the airflow stabilizes. From first pressure drop to stable flame, less than a second. From the cabin, it sounds like a series of explosive bangs and looks like the engine is coming apart. What's actually happening is a computer clearing an aerodynamic blockage before your brain can process what went wrong. Before any engine carries passengers, it has to prove it can survive all of this. Not in a simulation, but in a reinforced test cell, with a real bird and a real engine at full power. The device is exactly what its nickname suggests. The chicken gun, a pneumatic cannon aimed at the intake of a fully operational engine running at maximum takeoff thrust, firing euthanized birds at speeds matching takeoff velocity directly into the spinning fan. The bird must be thawed. A frozen bird behaves as a rigid solid, delivering a concentrated, shattering impact that doesn't replicate the fluid dynamics of a real strike. A thawed bird accurately reproduces the hydrodynamic shockwave of a live collision. Testing facilities regulate the core temperature of every surrogate to ensure the physics match. The certification standard, FAR 33.76, scales the required bird weight to the engine's intake area. The largest engines must survive an 8-pound bird without shedding shrapnel, without internal fire, without uncontained failure. But surviving the initial impact isn't enough. After a flocking bird ingestion, multiple birds fired in rapid succession. The throttle cannot be touched for 2 full minutes, simulating the time a crew needs to assess the emergency. Then the damaged engine must complete a 20-minute flight profile, varying power settings replicating a climb, a hold, an approach, and a go-around. the full sequence a crew would fly to bring a damaged aircraft back to the runway. If the engine can't finish, it doesn't get certified. Those certification limits exist because reality found the boundary. On January 15, 2009, U.S. Airways Flight 1549 hit a flock of Canada geese at 2,800 feet, 90 seconds after takeoff from LaGuardia. The geese weighed between 8 and 10 pounds each. Both CFM56 engines ingested multiple birds simultaneously. Every system responded. The centrifugal sorting worked. Both FADECs detected the surges and attempted recovery. But the sheer volume of dense fluid overwhelmed both splitter ducts at once. The compressor blades deformed. The variable stator vanes, the ones the computer needed to pivot, bent. The internal geometry the FADEC depended on was physically destroyed. Both engines flamed out. What followed, the unpowered glide, the ditching in the Hudson, all 155 people walking off the wings, demonstrated two things simultaneously. The containment held, neither engine sent a single fragment of shrapnel into the cabin or the wing fuel tanks, and the engineering had a hard physical boundary when the fluid volume exceeds what both bypass ducts can sort at once. No software intervention recovers it. Every major certification update since has pushed that boundary further. The required bird weight doubled from 4 pounds to 8 pounds. Run-on requirements expanded. But the lesson stands. The engine is engineered to survive the strike, not to be invincible. Next time you're walking down the jet bridge and you glance into that engine, silver leading edge, dark composite body, the wide nacelle housing a duct that doubles as a centrifuge, you're looking at a system built to survive a 70,000-pound fluid shockwave without breaking apart. Behind the blades, a bypass duct sorting debris by density at thousands of RPM. Behind that, a computer fast enough to reshape the engine's internal geometry before your brain registers the bang. And if you ever see that fireball from a window seat, the one that looks like the engine is finished, now you know what it actually is. A computer clearing a blockage, an engine that just saved itself. What's something else on a plane that looks like it shouldn't work but somehow does? Drop it in the comments.